Earlier we said there's about 4 steps in determining the empirical formula of a compound if we're given percent composition data. Step 1 was to assume a 100-gram sample, because then I can get those percentages into grams. Step 2 was to convert grams to moles, because moles is a unit that represents a quantity of particles, and that's eventually what I'm looking for. I'm looking for this whole number ratio of atoms in a compound. Moles is a unit that will do just that. It'll give me a ratio of atoms. Step 3, if your moles don't end up being whole numbers, we want to try to find the lowest whole number ratio. First step to try is dividing each moles by whichever one is smaller. Hopefully that fixes it for you. And then finally, once I have that whole number mole ratio, that ratio becomes my subscripts in the final formula. Here's another set of data that kind of walks you through those steps. Someone has a compound that is 25.9% nitrogen and 74.1% oxygen. We want the empirical formula. All right, well, step 1 was to assume a 100-gram sample. If you have a 100-gram sample and it's 25.9% nitrogen, that means you've got 25.9 grams of nitrogen and 74.1 grams of oxygen. Now again, we kind of said you could assume whatever sample size you want, but it's just really easy if you assume 100, because then those percentages automatically become your masses. If you want to assume that you have a 243-gram sample, that's fine, but then you'll have to multiply your 243 grams times 0.259 to figure out how many grams of nitrogen would be in your random sample. So 100 is just easiest. All right, once we've got grams of each element, we want to switch grams into moles. And that's what we've got down here. Take each of those grams, cancel grams, which is just your molar mass on the periodic table. We want moles on top, 1 mole. So we're going to divide. And then we get moles of each element. Okay, cool. Well, here I get 1.85 moles of nitrogen and 4.63 moles of oxygen, which are obviously not whole numbers. Okay, well, then step 3, is to divide each by the smallest, which is kind of what they did up here. So if I were going by the earlier steps that we looked at, maybe this is kind of like step 1. This is like step 2. Here's step 3. Let's try dividing each of your moles by whichever one is smaller. And then you cross your fingers and you hope for a whole number. Well, obviously 1.85 divided by 1.85 is going to give us a whole number 1. And often your other element will come out to be a whole number as well. If not, you might get something like this, where, oh man, I divided them both by the smaller moles, and I got a ratio of 1 to 2.5. No, bummer. But we can make that a whole number ratio. It's just that I can't have 2.5 atoms of oxygen in my formula. So if you get something here that's like a 0.5, then just multiply both by 2. And you have to still keep the integrity of the ratio. The ratio is supposed to be a ratio of 1 to 2.5. So I have to multiply both of them by 2, so that a ratio of 2 to 5 is equivalent to a ratio of 1 to 2.5. It's just that in a formula, I need the ratio to be a whole number ratio. And so this is maybe like step 4 now. That once I've got a whole number ratio, that mole ratio becomes my subscripts, N2O5. There it is. So here's a really good example of maybe the worst it ever gets, where you take your percent, you turn into grams, then you take your grams, turn them into moles. If you don't get whole numbers, try dividing them by the smaller of the moles. That usually will solve the problems. And if not, you get something like this, where you got a 0.5, or let's say I divided them by the smallest and it ended up to be like 1.333333 repeating. Well, then I can just multiply them both by 3. Once I have whole numbers, that becomes my subscript. Let's try another one. Calculate the empirical formula for a compound that contains mercury, sulfur, and oxygen. All right, let's do it. So if I had a 100-gram sample, then I would have 67.6 grams of mercury. And I would have 10.8 grams of sulfur and 21.6 grams of oxygen. There's step 1. This is easy so far, right? Step 2 is to convert all these guys out of grams and into moles. So here's one of the places where we use that mole stuff. We want to get a unit that represents an amount of particles. We want a ratio of atoms in our final formula. That's the mole. On my periodic table, then, I can look up the molar mass of mercury, 200.59. And I'm going to set up each one to cancel grams, put her into moles. 1 mole has the mass on my periodic table. Mine says about 32.07 for the sulfur. And then I'm going to cancel grams of oxygen. I want moles of oxygen. 1 mole on my periodic table is 15.999. Now I get that some of these are really close to a whole number, but I don't know. I usually just leave a couple decimal spots. I mean, maybe I would have rounded the oxygen to 16, depending on my mood for the day. But I'm okay leaving a couple decimal spots here. And in fact, I usually like to go at least 2. Then I just feel like I'm getting the most precise answer. Same thing when I plug these in my calculator. I'm gonna maybe leave 3 digits. The original measurements, the original percentages were given with 3 digits. So maybe I'll kind of leave about 3 divided by 200.59. So I've got about 0.337 moles of mercury. I'll take my 10.8 divided by 32.07. Oh, look at this. 0.337 moles of sulfur, and 21.6 divided by 15.999. This one's kind of weird. 1.35 moles of oxygen. All right, step 1 was to assume a 100-gram sample. Step 2, get your grams into moles. Step 3, we want a whole number ratio, which these are not whole numbers. Now, obviously, the mercury and sulfur are probably going to end up being 1-to-1s, but I'm not really sure about that oxygen. So we divide each by the smallest, 337, because I know this is going to be a 1. Divide by 0.337. It's got to be a 1. And then I'm going to do the same thing here. Divide by 1.35. I have, whoopsies, divide by the same, the smallest. My bad. 0.337. I have no clue what this is going to be, but if we plug it in, I'm just hoping that it's a whole number. Yes, 4.0059. That's close enough to a 4. Now that's my whole number ratio of atoms in the formula. So I can write my formula as Hg, there's only 1. Sulfur, there's only 1. Oxygen, there's 4. This is mercury sulfate. Now often we end up doing this with transition metals because transition metals have different charges and we have to use the data to kind of figure out what charge was used so I could write the formula. So if I was really curious, I know the sulfate group, if I look it up on page 98 or whatever, The sulfate group is -2. And so there's only one sulfate, SO4. There's only one mercury. So to make this neutral, mercury must have been +2. This was mercury 2 sulfate. So these are great. They're just very methodical. You set every one up the same way. Assume 100 grams, get your grams into moles, divide them by the smallest to get that whole number ratio. And worst case scenario, maybe I would have divided them by the smallest and I would have gotten like a 1.5 or a 0.333. Well, then I could just go through and multiply them all by 2 or all by 3 to make it a whole number ratio. Then you've got the ratio of atoms in your final empirical formula.